Okay, YouTube, in our last video, we looked at these fundamental trig identities and we discussed how we could use them to evaluate trig functions. In this video, what we're going to do is look at how we can use these fundamental trig identities to simplify or rewrite expressions that, as they are, might seem complex but could be written in a little bit simpler way and also mean the same thing as what we started with. And so what we're going to do is we're going to tie in all of our identities in this video. And with respect to our identities, let's recall that we have our reciprocal identities, tangent and cotangent identities, and Pythagorean identities as being our pretty standard ones. But in this video, we're going to build on what we refer to as our cofunction identities as well as our negative angle identities. So let's go ahead and hit our negative angles first. This is pretty quick. But basically, we're going to say that cosine is the only even function. And it's not so much that you need to know it's even as much as you need to know that when we take the cosine of a negative, it is the same thing as if we take the cosine of a positive. Whereas when you look at sine and tangent, okay, these are odd functions. Again, it's not so much that you know that they're odd as much as that you know when you take the sine or the tangent of a negative, we still rewrite this as the sine or the tangent of a positive angle, but you notice where the negative front and basically, or where the negative went, it got carried out in front, okay? So when you take the sine or the tangent of a negative, we may carry that out in front. So with respect to our cofunction identities, I want to rewrite this a different way. Basically that the sine of 90 degrees minus some angle would be equal to the cosine of that angle. And that's just a testament to if we had some triangle, and I'm going to throw this together pretty quickly here, we'll call this A, B, C. We'll call this lowercase a, lowercase b, and lowercase c. But what I want to understand is that angle A and angle B, if we were to say what's the measure of angle A plus the measure of angle B, basically what I want to admit to is that they always have to add up to be 90 if this is a right triangle and the other 90 degrees are down here. And so if that's the case, check this out. If we were to do, say, the sine of angle A, sine, right, SOHCAHTOA, that'd be opposite over hypotenuse, we get A over C. And if we were to go up now to B, and not do the sine of B, but the cosine of B. And cosine, of course, is adjacent over hypotenuse. So in this case, we get A over B. A over C, excuse me. What you understand pretty quickly here is that whenever you do the sine of one of the acute angles, and then you walk over and you do the cosine of the other acute angle, you always get the same thing anyways. And so if A plus B equals 90 degrees, then it must be true that just the measure of angle A, if I were to subtract the measure of angle B over to here, basically I would get this. I would get 90 degrees minus the measure of angle B. And so, long story short, it basically means that whatever your angle here is, it's 90 degrees minus the other angle in the triangle, okay? And so what you're seeing essentially is that sine and cosine, we'd say cosine, whatever it is, it's the same thing as the sine of 90 degrees minus your angle. And what we're saying is that this angle right here is complementary to angle theta. And so if that's the case, then really what we're doing is we're saying if you took the sine of one angle here, you get the same thing as you take the cosine of this. Likewise, okay, we have the tangent of an angle is equal to the cotangent of its complement. And likewise, the cosine of, the sine of an angle is equal to the cosine of its complement. So these first two are kind of backwards of each other. And tangent and cotangent share the same relationship. So using these, what I'd like to do is kind of play around with these expressions that we see up here and kind of see if we could use them to rewrite these expressions using what I know on the left here. And so I'm going to write down some suggestions, starting with this. One is this, manipulate algebraically. Okay? And what I mean by this is like distribution. Distribution, that's also, sometimes we refer to FOIL is what we're doing. Two binomials, we're going to multiply those by using FOIL, but that's also distribution. But also like factoring, can we factor anything out that they have in common? The other thing we're going to do is we're going to look for easy identity substitutions. That is, as we have this list over here on the left, are there any things that we could rewrite? Okay, just using one of those. And then the last one here is this, convert all trig functions into sines and cosines. I'm going to try to squeeze this in here. Cosines The reason why is because we might see some things that cancel out pretty easily. So with respect to letter A up here, it says, would you please and thank you, would you simplify 1 plus the cosine of theta times 1 minus the cosine of theta? And so of course I mentioned down here that, maybe we play around with this, we FOIL it out, and we see what we can get to happen here. So let's do that. We say 1 times 1, certainly we get 1. Now if you took 1 times a negative cosine theta, that'd just be negative cosine theta. Cosine theta times 1, that would be a positive cosine of theta. And then we have cosine theta times a negative cosine theta, well that'd be negative, and cosine times cosine is cosine squared. So looking at this, what I notice is that my cosines cancel out and I get left with 1 minus cosine squared of theta. So with respect to what we see here, I say, well, could I do anything else with this? Could I factor it? Well, it factors back into its original form. Nothing else to multiply by, So maybe we can look for easy identity substitutions. And what I remember about all my identities here, the Pythagorean ones had squared terms on them. So maybe I'll go look at this here. I'll say go to the Pythagorean identity that has a cosine squared. So looking at this right here, what I notice is that it certainly does have a cosine squared, but this up here is 1 minus cosine squared. And I want to know, well, what is that the same as? And so since that's the case, I want you to look back at this identity. How could we rearrange this to make it look like a 1 minus this cosine squared? And I hope you see this here. What we could do is we could subtract cosine squared over to the right side, and what I end up with is 1 minus cosine squared of theta means the same thing as just a sine theta. So all in all, this original expression up here, what I got to tell you is it would really mean the same thing as a sine squared of theta. And you say, well, okay, well, what's the big benefit here? Essentially, we were able to write something that is complex as a single term or a single expression, which is kind of a nice thing. So we have sine squared of theta. Okay. So letter B looks like, can we distribute? No distribution, no foiling, no factoring. Could we use some easy identity substitutions? And so looking up here, well, I noticed cotangent and tangent. Let's remember using these identities that tangent's sine over cosine, and cotangent is cosine over sine. So perhaps what we do here is this. We're just going to take our cotangent and tangent out, and what we'll do is we'll replace our cotangent with cosine of theta over the sine of theta. And I'm going to replace the tangent of theta as the sine of theta over the cosine of theta. So now looking at what we have here, this is going to go back to what algebraic manipulation we can do, but we could add or subtract fractions. Okay, and I'm going to make a little note here underneath add and subtract fractions. We need a common denominator. So need a common denom if we're going to do this here. And so when I look at this here, by the way, looking at step 3, if we would have been stuck by using easy substitutions, notice it says convert all trig functions to sines and cosines. That's exactly what we've done here. So with respect to our common denominator, what I know is this. It's going to have to be the product of these two denominators down here. It's going to have to be a sine times a cosine. So what that means is over here, we're going to take both the top and the bottom times the cosine of theta. Really multiply by 1. So we're going to multiply top and bottom times cosine of theta. Here we're going to multiply top and bottom times the sine of theta. And in this case, what we end up with then is if we rewrite this here, we would get cosine times cosine, or a cosine squared of theta, and that would be over a cosine sine. And this is now plus. We get a sine times a sine, so a sine times a sine is a sine squared of theta. And this is over a cosine times a sine. So now we end up with this guy here where we've got a common denominator. So what I'm going to do is I'm going to put everybody over the same denominator here. We've got cosine of theta times a sine of theta. Cause this to happen. And on top we get cosine squared theta plus the sine squared of theta. So one thing I want to point out to you is this. Your brains, I hope, get really excited when you see this expression cosine squared plus sine squared, because what do we remember about cosine squared plus sine squared? Well, sine squared plus cosine squared is always equal to 1. So the fabulous thing about this entire expression right here is that we can just rewrite this as 1. We're going to substitute a 1 in for cosine squared plus sine squared. And this is all over cosine theta sine theta. So my last little maneuver here is something that, because I've practiced this a lot, I kind of know that this is what we want to go for. But I do want to show you this here. Whenever you have, say, 1 over these two factors in the bottom here, we could rewrite this as 1 over the cosine of theta times 1 over the sine of theta, since multiplying those together would get us the same thing anyways. And the reason why I'd like to multiply these together, but rewrite them this way, is because 1 over cosine of theta really is the secant of an angle, and 1 over sine of theta really is the cosecant of an angle. So long story short, our original expression here, cotangent theta plus tangent theta, could instead be rewritten as the secant times the cosecant of that angle. So now in this last one here, what we want to do is simplify these two expressions. So it looks like we have a tangent of pi halves radians minus theta times a sine of theta. So looking at this, it doesn't look like we have any distribution that we can do. We can't send this through because this is an angle right here. So we can't distribute, we can't FOIL, there's no factoring, and we're not adding or subtracting fractions. So looking at our second thing here, we say, could we find any easy identity substitutions? So looking at this, let's look at how we have a tangent of pi halves minus theta equaling a cotangent of theta. So what that means is all of this right here, what we're going to do is we're going to try replacing it with just a cotangent of theta and take that times a sine of theta. So now we have this expression cotangent times sine. Is there anything else we can do with this? Well, I would encourage us to remember that the cotangent of an angle really is the cosine of that angle over the sine of that angle. And if we're taking all of this here times the sine of an angle, I'm just going to put that sine of an angle over 1. What you see happening is that our sines cancel out, and we just get 1s there, and we get left with the cosine of theta. So long story short, this original expression here can be rewritten as a cosine of theta. And then with respect to this last one here, we have secant theta plus tangent squared theta plus secant of theta. Maybe what I'll do is I'll put that up here. I'll rewrite it up here. We have secant of our angle times the tangent squared of our angle plus a secant of our angle. So again, let's look at this. We say, look, is there any distribution that we're doing or any foiling that we're doing? Okay? And I don't notice that we have anything, but what I do notice is that when you look at this term here that I'm adding to this term, they both have a common factor of the secant of theta. So what we're going to do is we're going to factor out the secant of theta, we'll take it out in front, and what we get left with on the inside would then just be tangent squared of theta from this term plus now, and we have to put a placeholder here, so we say plus 1. You can see that if we distributed the secant through again, we get the original expression. So the benefit to doing this is because the tangent squared plus 1, that looks very Pythagorean, and when you look down here at tangent squared plus 1, what we see is that's the same thing as a secant squared. So instead of secant theta times tangent squared plus 1, we're going to say secant theta times a secant squared of theta, which comes out to be, really, secant cubed of theta. Cheers.